Okay. So good afternoon all again, and welcome back to the another lecture of SEM 1 Electronics paper 2, and we were working on number systems, I guess. So we'll continue with that, and for that I have just to present the revision of this number system, that whatever we have studied up till now, and then we'll continue with the next topic of the number system itself, right? So let us begin. Let me share my screen. Uh, Let me share my presentation on that. So yeah, so I guess my screen is visible to you all. Uh, yes. So let me introduce myself. Myself, Dr. N.D. Meshram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mohta College of Science. And uh, myself, as I told you, Dr. N.D. Meshram, Head and Associate Professor, Department of Electronics. And today we are going to learn about the revision of number systems. So we'll be working on that. And yeah, so we'll be working on this number system that we have. Manish, please delete kar do wo. uh, ठीक है, then I guess, thank you, Manish. So yeah, so we have started with this. There are various number systems that we have. The first one is the decimal number system that we have studied up till now. We have gone through that, and then the binary number system. So we have hexadecimal number system, we have octal number system, we have gone through all those. So let us compare this uh, decimal and binary number system. So I guess it's not working. So it has lost. Okay. Yeah. So this is the basic of the decimal number system that we have. And yeah. So the positions of this is thousands, hundreds, tens, and units place. So we have this 10 raised to power 0, 10 raised to power 1, 10 raised to power 2, and 10 raised to power 3. And we have their values as 1, 10, 100, and 1000 respectively. So this is what uh, we have. So these are the numbers which we represent in the decimal number system, and we have studied up till now. And this is a very easy thing that we do. And the other one is uh, integers and their binary equivalent. So we have this 16. We have made this table. Those are, of course, those are 16. Hopefully I've told you to make this table of 16 numbers, mm, from 0 to 15. I have told to do that. So the equivalent of a decimal zero is, in binary, is zero, 4 is 100, 5 is 101, 6 is 110, 7 is 111, and 8 is 4 bit, that is 1000, 9, 10, 11, 12, and 16. Likewise. So this is what we have studied. And for binary, what are the positional weights and their values in decimal are shown over here in this table. 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, and same 2 raised to power 7, and their decimal value, the equivalent values. So we are having this, and how they can be converted is shown over there. So this particular binary number is to be converted into decimal by using this pattern. Yeah, we have studied. I'm just brushing it because we already know this things. So these are in the form of presentations. But when we actually study it on the blackboard, then only we will be able to see how it works, right? So I have shown you that, and we have understood this conversion. That is from decimal to binary, and say from binary to decimal. Right. So then converting a decimal to binary, how we are going to convert a decimal number to binary? I guess you have known this. We have studied this in the last class. That the method is called as the double table method. That is uh, sum of powers of two. So we'll have this. will convert like this. So 1011. So that is the number 11 is to be converted over there. And how we are going to convert this? We are going to convert by using the double double method, right? So that the method is called as the repeated division or double double method. This is what we have studied in the last classes, right? Here it is shown that we are having two, we have having this number 418, and we are dividing it by 2, and we are storing the remainders over there, which is supposed to be the 1. So we are storing them, and we are restoring this from, say, down bottom to top, right? So we are writing like this, and the number appears like 837 can be written as 1101000101 of binary. This is how it is represented. So this stands for the radix or base, which I need to tell you, which I already told you, and this two implies that this particular number is a binary number, right? So whenever we are having 2 in the base, that particular number is supposed to be is considered as the binary number. Whereas whenever there is the radix or base of 10, then that particular number is considered in the decimal number system. Like, so these are things which we have already studied. Then, yeah, binary numbers and computers. Yes. So we have to correlate these binary numbers. We have to use these binary numbers in computers. Now, how they are going to represent or how you are going to use those. So the letter A, which we type on the keyboard of the computer, this represents a decimal number, which is 65. I'm going to show you that numerical table, and the code of that particular number is 7-bit binary representation is like this. So 1000001, right? So 65 is actually the decimal number which is represented by the alphabet A or on the keyboard. Then it is coded to binary like this. So we are having a 7-bit number generated when we press A on the keyboard, right? And likewise A, B, C, D, E, F, I, G, and so on. So those numbers we'll see these numbers also. We have some more numbers. So the hexadecimal number. So hexadecimal number is having these symbols, that starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F, right? So these are the hexadecimal numbers, means 15 symbols we are going to use from 0 to 15, and therefore it is called as a hexadecimal number. So this is a number 13A7, which is being converted to, say, decimal in this. So it is shown how it is being converted. So it is 1, so 1 into 16 raised to power 3, 3 into 16 raised to power 2, A into 16 raised to power 1, and 7 into 16 raised to power 0. 16 raised to power 0 stands for 1. 16 raised to power 1 is 16. 16 square is 256, and 16 cube is 4096. And when we multiply these all and add them, we get this number as 5031 of decimal. So this is how you are going to convert a hexadecimal number to decimal. Similarly, whenever we need to convert decimal to hexadecimal, again we will use the same sort of method that we have used in the binary conversion here, but the change is we have to divide the decimal number by 16. So 8123, here we have divided it by 16, and we will save this, will save the remainders over there. So 8123 by 16, and if you are able to see, they have generated some fractional numbers over here, and then they have multiplied it by 16. So you'll get this remainder. That is one of the way, or you can divide it, and directly if it is less than 16, that you can write. So you don't need to divide the whole number as such to get a fractional output. But yeah, this can be a method to convert that. So 0.6875 multiplied by 16 will give you 11, and 11 in decimal stands for B in hexadecimal. So we are going on converting like this, and if it is less than 16, then we'll leave the last bit as it is. So the number is 1FBB, right? So 8123 of decimal can be converted to hexadecimal, like 1FBB of 16. Again, we have written the radix or base as 16. So converting a hexadecimal to binary, it's a very simple method. We have to form the group of four, and we have to write the equivalent of that. So binary number to hexadecimal is little bit easier. We have to divide 16 bits, sorry, 4 bits group, and that particular 4-bit group is given a particular code accordingly as per the table that we have already uh, made. So if you are able to see over here, this is that number 1010001100001 and 000. So we are making the 4-bit group, and we'll be writing the equivalent of that particular 4 bit. So this stands for 0, this stands for 1, this stands for 6, this stands for 4, and this is 1 itself. So this is again 001. So I'm writing 1. So the total number comes out to be 14610. 14610 of 60. This is how we convert a binary number. In binary to hexadecimal conversion, we have to take 4 bits of group, and then we have to make it hexadecimal number. Again the same. I need to show you this table, because where we are going to use that particular hexadecimal number. Now this hexadecimal number, if you are able to see, these are some of the characters which are there on the keyboard of a computer. So these type of hexadecimal numbers are being generated by a particular code, particular key which is pressed on the keyboard, and this key is then decoded by the CPU, and accordingly it processes the action, or it takes the action what is to be printed on the screen, right? So whenever you do this, whenever you press the keys on this keyboard, you'll be having this type of a alphanumeric structure. Here I need to show you that the characters over here, that is A, the hexadecimal equivalent is 41, and the decimal equivalent is 65, as I showed in the earlier slide over there. So we have all these characters A, B, C, D, E, F up to Z. Then they will have small characteristics A, B, C, and so on. So there are many codes which are generated over there, and then they are being converted back again to binary numbers, and then binary numbers are being used for processing. So we might use a hexadecimal number, we might use a decimal number, but the computer understands only the binary number system. So it's not going to change, right? So yeah, this is actually which shows you what are the applications of a binary number, or a hexadecimal number, or a decimal number for a layman, or say for a programmer which who is very comfortable with decimal number system, should understand what character we are having and what is its decimal equivalent. So that is going to be shown by this table. So there are these characters which are there on the keyboard, generates these types of hexadecimal, decimal, and binary number codes, right? And then only they are being interpreted over there. So these are some of the binary arithmetic that we have studied. Some rules of binary addition I have already discussed with this. So this is 1 plus 1 is 1 0, 0 plus 0 is 0, 0 plus 1 or 1 plus 0 is 1, and here we have given 3 bits to add all our ones. So 1 plus 1 is 1 0, plus 1 will give you 1 1. So include the 1 carried from the previous column to the right. So we have taken 1 carry with 1. So the say the output of 1 plus 1 plus 1 is 1 1. This is what the rules of binary were. I have already given it on the WhatsApp. And then we are having, there are some challenges also on representing the integers. So the integers can be positive or a negative. So this is the basic difficulty, how to represent a positive or a negative number. Then each integer should have a unique representation, right? So these are some of the difficulties that we face. The addition and the subtraction should be efficient, right? So the circuits that we are going to develop by using these binary codes, which I have told you, those are called as say full adders, 4-bit full adders, 8-bit full adders, and 8-bit subtractors. So we'll be generating or we'll be implementing some of the circuits on that by using logic gates. So they must be efficient. Then yes, representing a positive number. This is in your syllabus. So how you are going to represent a positive number in binary? So this is how you are going to represent 0 up to 7. And in this, if you are able to see, this first bit represents the sign of that number. This first bit, if it is 0, then we consider it as a positive number. And if it is 1, then the number is supposed to be a negative number. So I have written here the decimal number that starts from 0 to 7. And this MSB, we call it as MSB, most significant bit or most significant digit in that case, so is considered as the sign. So whenever we call say that this is a signed number, so the first bit will represent whether it is a positive number or a negative number. We'll show you some more. So if I need to write -5 over there, so I have to take this MSB, that is the most significant bit, as 1. And this represents the magnitude of this bit. So fourth bit is sign, and the other three are the magnitude of that number. So this will represent minus, and this will represent the exact value. 101 stands for 5 in decimal. 101 in binary stands for 5 in uh, decimal, right? And this now this one represents the negative number, that -5. There is one more, that is -55. So here we are having the magnitude of 7 bits, that is 0110111. So this stands for the value of 55 in decimal, and this one again is going to represent what is the sign of that. And if it is negative, then it will show you that this is a negative, yeah, -55. So 8 bit will be the sign of that number, right? Okay. So just for a second. Yeah. So ones and twos complement, we have already studied how to convert a ones complement. Now, how to convert a positive number, ones complement representation of a positive number at the same as sign magnitude. So plus 84 can be written as like this. Yes. Okay. Sorry. So we have, yeah. So plus 84 can be written as this. 0 1 0 1 1 1 0 1 1. And now if we need to represent the ones complement of a negative number, then how we are going to represent? So subtract the magnitude from 2 raised to power n minus 1. For example, uh, yeah, -36. So plus 36 is written like this, and it's 3 plus 6. We are working on BCD codes. So if you subtract 111 by -0010 and this, so you'll get this number 11011011. So this represents the negative ones complement of that negative number. So this is one's complement, and these are some more examples of tests. Yeah, here we have shown that this is the plus 57, and this is for -57. So the ones complement of 57 is this, and the negative 57 is like this. So both are same. This is converting to decimal format. uh, yeah, you know the weightage of these binary numbers, and accordingly we put that, sorry, we put the values and add them, and these are some binary numbers. So I guess, and these are some two's complement methods. So subtract the magnitude for 2 raised to power n. Likewise, we have done with this. So if you add, so this is that binary answer in byte. So 70 is written like this. No, it is 46, right? So when you once you take one's complement, then you will get this number, and if you add one to it, you'll be having the two's complement of that particular number 7, right? So therefore, we store the integer negative sign or 70 in byte in two's complement form as 1011 and 1010. So this is what we have already done. uh, we have done this to negative numbers and decimal number. So the first bit of binary, the MSB of the binary number is taken as the sign of that number. Whether if it is zero, then we take it as positive number. If it is one, then we consider it as a negative number. This is the two's complement number, and this is what I need to show you. This is a 8-bit um, adder subtractor circuit. This is an arithmetical logical unit which is there in the CPU of a computer, and this is how it is going to add two 8-bit numbers. And if there is a overflow, then it is going to show you like this. So this was the concept of having this. Why we are studying binary numbers, because binary numbers are easy to process, right? So we need this adding positive integers in two's complement. We have done all these things there. So I guess we can continue in the next class. These are how the some of them are overflown and done this. So by for today, I guess it is okay. We might continue in the next class, and we'll try to study gray codes, right? So gray conversion, we have they are in the pipeline. I guess it's not working only. So yeah, my mouse is not working. Yeah. So overflow, binary addition, then we are having some two's complement and three's complement. Uh, these are some adding, subtraction, digital codes, BCD codes we have studied there. So these are BCD codes, how to convert those BCD codes. And yeah, 4221 code, 8421 code, I have told you. And this is the gray code that we are expecting to teach you. So this is how the conversion is there, gray to binary and binary to gray. So I'm going to tell you how you are going to convert a binary number to gray and gray to a binary number, and what are the applications of it. So I guess for today it's in more than enough. We have just revised what we have studied up till now, and in the next class we'll continue with this. Again, I will show you. Uh, uh, I will teach you again this presentation, and say in the next class we'll be completing gray code and say the access 3 code as well. So by today, if you have any questions, you can ask, or we can end the class on that note. Or let me end the meeting formally. So yes, thank you very much for joining this class, and I hope you have understood the number systems that we have studied earlier. We have just revised what we have studied up till now. In the next class, we are going to study the further of this, that is the gray code and access 3 codes, which are supposed to be the last topic of this unit, and we'll be completing this at the earliest. So thank you very much for joining. Thank you very much for viewing my video. Go through my YouTube channel and watch more videos on number systems. Thank you very much. Have a nice time. Stay home, stay safe, and take care. See you soon. Bye in the next class. Good day.